This is the formula for the interval estimate of the difference between two population means when the population variances are assumed to be equal. We call this the pooled variance method. So this is the part that's different than the confidence intervals we've been looking at. And the S subscript P comes from here. So this is the pooled variance. So S squared subscript P for pooled. And so that's the pooled variance. And if you take the square root of that value, it equals the pooled standard deviation. So just S subscript P, and you plug that in to the formula. That is what goes in there. The degrees of freedom, you take the size of sample 1 plus the size of sample 2 and subtract 2, and that's what you use for the degrees of freedom. Now you only want to use the pooled variance method when the ratio, so the standard deviation for sample 1 and the standard deviation for sample 2, those are the sample standard deviations. If their ratio is between 0.5 and 2, then it is okay to use the pooled variance method. Otherwise, use the non-pooled variance method. The non-pooled variance method is what we've been using up to this point. So I'll just go back to refresh your memory. So this here is the non-pooled variance method. This is the difference right here. We use this square root. That was the standard error. And so the standard error is different for the pooled variance method. You can see right here the difference. So this is the standard error for the pooled variance method. Okay, so we will look at an example, and we will revisit the Bank of London example that we used earlier. So construct another 95% confidence interval for the Bank of London data using the pooled variance method, and we'll then compare the two intervals. So let's just I'll go back again, and we will look at the Bank of London example. There it is there. So we were looking at two different branches, and we were looking at the difference between the checking account practices by customers at two of its branches. And so random samples were obtained, and the summary of the their account balances are in the table here. So we have the sample sizes for branch A and B, we have the sample means, and we also have the standard deviations, which I have put in here, subscript 1 and subscript 2. We need those for the standard error for the pooled variance method. So we'll use these numbers. We're going to use these sample size, means, and standard deviations to go into our new confidence interval. Okay, so first thing you want to do is calculate the pooled variance. So I'm just going to plug in the values that we just saw on the table. So the sample variance, we want to square that to get the sample variance. And then 28 subtract 1 is 27. And then for the branch B, we want to square that because that was the sample standard deviation. And then 22 subtract 1 will be 21. Divide by, now the size of sample 1 was 28. Sample 2 was 22, and we'll subtract 2. Notice that the denominator is the degrees of freedom that we use. It ends up being 48. So that equals 9,035 and 625 divided by 48. That's the degrees of freedom we'll use right there, 48. And that ends up being 19,492. And I'm going to carry lots of decimals because I'm going to be getting the square root. So the square root is what I need for the standard error, or for the standard error. So let's see here. So we want to take the square root. That will give us the pooled standard deviation. We'll just plug that value in that we calculated. So 19,492 decimal 1875. Take the square root of that, and we get 139.61. All right, now we can calculate the standard error. Now remember, this is the standard error of the pooled variance method. it is different than the standard error of the non-pooled variance method. So we can just plug in 139.61 that we just calculated, and then we want to get the square root of 1 divided by the size of sample 1, and then add that to 1 divided by the size of sample 2. Okay, this section right here, you might want to do it separately. That ends up being 20.2849, and that equals 39.78. Okay, so the 95% confidence interval, we still want to get t. So we want to figure out t. It's a 95, so that would be 0.25, 48 degrees of freedom. And we will go to the table, and we can see that we want this column right here. And notice we do not have 48 degrees of freedom. It goes 30, 40, 50. So always round down. This will give you the larger t. If you round up, you'll get a smaller t, so it's best to err on the side of caution and use the larger t. So always round down if your degrees of freedom is not on the table. So that's the value we will use, 2.021. So that's going to be t of 0.025 of 40, which equals 2.021. And we're ready to go now. So x bar 1 subtract x bar 2 plus or minus, we're going to put in the t there. We'll put in t times the standard error. So that ends up being, using the data, the Bank of London data, will be $115 plus or minus the standard error. So the standard error has this t, 2.021, and so that's the margin of error for the t value, and the standard error will be times 39.78. So that's the margin of error, $115 plus or minus 78.37438, lots of decimals. All right, so that ends up being $36.63 to $193.37. So 36.63 to 193.37. If we compare that to the confidence interval that we calculated for the Bank of London using the non-pooled method, we got, it was 3407 to 195.93. So look at the difference. We can compare those two. We can compare that one to this one, and we can see that whenever we use the non-pool, or whenever we use the pooled variance method, this one here is more narrow than the one using the non-pooled. So what happens when we use the pooled variance method, we produce a more narrow confidence interval. So that means it's more precise, but to err on the side of caution, it's better to use the non-pooled method unless you know for sure that you've calculated this condition, then it's okay to use the pooled variance method, right? And it's safe to do. So we end up with a more narrow confidence interval than we do with the non-pooled variance method. Okay, so that's the difference between the two intervals.